So we saw that in the different noise models, the noise are described in spatial domain in terms of the statistical behavior of the intensity values that the noise components take. So every noise model is basically a plot showing the probability density function, in which the noise component intensity is the random variable shown in the horizontal axis, and the vertical axis in each model is the probability of the different intensity values that the noise component may take. Although we have discussed 6 types of noise models, the most common noise models, there are many other noise models also, but we have discussed the 6 most important noise models that are quite popular in image processing applications. So we discussed the Gaussian noise, the Rayleigh noise, the Erlang noise, the exponential noise, the uniform noise, and the impulse noise. In impulse noise, we have taken the case of bipolar impulse noise and the unipolar impulse noise. But it is to be noted that in general, the intensities, the two intensities that we have represented here, the intensity A and B, they are free to take positive or negative values. Now let's say A can be a negative value. Both A and B can be negative. A can be negative, B can be positive. It may so happen that both A and B are positive. So we have to be free to think, to allow that the intensities A and B can be both negative and positive quantities. And since impulse corruption is usually of much larger magnitude than as compared to the value of the image signal, or you can say the value of the pixel in a particular image, and so impulse noise is generally digitized to the extreme values that is ever allowed in an image. So we model the A to take the least allowed intensity that is allowed in the image, and let B to take the maximum intensity allowed in the image. So if we have a intensity range of 0 to L minus 1, A is equals to 0 and B is equals to capital L minus 1, L minus 1. So in an 8-bit image, in general, a bipolar noise will be modeled with A equals to 0 and B is equals to 255. Of the 6 kinds of noise model that we have discussed, it is not so that whatever may be the kind of noise that is corrupting an image, we can take into account any noise model. We can take any noise model and put that particular noise model into that application. It is not so. We have to very cautiously, in a very decisive manner, we have to choose a particular type of noise model that is most closest to the noise that is actually corrupting the image in that particular application. So whenever we'll have an image that is corrupted by a noise, whose source is circuit noise or sensor noise due to high temperature or poor illumination, in that case such noises are best modeled by the Gaussian noise model. Similarly, images from range imaging, in such kind of images the noises are best modeled by Rayleigh noise model. What is range imaging then? Range imaging is such a modality of imaging in which the pixel intensity value at a particular point in an image is directly proportional to distance of the sensor from the particular point in the scene. So intensity is directly proportional to the distance of the sensor from the point in the scene. Such imaging is called as range imaging, and whenever we are trying to model noises in range imaging, the Rayleigh noise is the best noise model to choose. Whereas when the image is acquired from a laser imaging equipment, in that case, if it is corrupted by noise, such noises are best modeled by exponential and gamma noise models. And when the noise is due to quick transients, just like faulty switching during imaging. If there is some faulty switching, and that's why any quick transients are taking place that may reflect upon our image as noise disturbances, and it corrupts the image with noise. Such noises are best modeled with the help of impulse noise model. So we should be very decisive in choosing which noise model to apply in what particular type of application. So noise model is has to be chosen on the basis of where the noise is, what is the source of the noise in that particular application. Now we will start off with an effort to restore a good estimate of the original image from the given degraded image. So here we will consider that our given image g of xy. So the degradation in our given image is only due to the noise and not due to a linear position invariant filter model. So we can express the degraded image, the given degraded image, as g of xy is equals to f of xy plus eta of x comma y. In the degradation model, we have been in general representing g of xy as f of xy convolution h of xy plus eta of xy. So here in this special case, here h of xy is a unit impulse. So f of xy convolution unit impulse is the f of xy itself, and so here the degraded image is g of xy equals to f of xy plus eta of x comma y. So what you should note here is the degraded image is only degraded due to the presence of additive random noise eta of x comma y. In the same thing when this is a thing in spatial domain. So the same above equation when expressed in frequency domain can be expressed as capital G of u comma v equals to capital F of u comma v plus capital N of u comma v. In a similar way, we can compare this expression with the general degradation model where we expressed capital G of u v equals to f of u comma v multiplication of capital H of u comma v plus capital N of u comma v. Here in this special case, your capital H of u comma v is equals to 1. So that is why f of u comma v multiplied by 1 gives you capital F of u comma v only, and so this is capital G of u comma v equals to capital F of u comma v plus capital N of u comma v. So here this is the frequency domain equivalent expression corresponding to this spatial domain expression. So what here we are assuming that the corrupted image given in spatial domain by small g of x comma y or given in frequency domain by capital G of u comma v is corrupted or degraded only due to the additive noise and not due to a linear position invariant filter model. For the degraded images which are corrupted only due to the presence of additive noise, spatial filters can be a very good choice in order to when we are trying to restore the image from its degraded version. We have already taken help of spatial filters while we were studying image smoothing and image sharpening by using spatial domain filters. So there we saw that there is a use of a kernel, or you can say the window or template, the same thing. So you take help of a certain m cross n window in order to implement a spatial filtering. So what we have been doing in spatial filtering, to revise it, just let us just rediscuss it. We define a kernel of size m cross n. Let in this case m cross n be equals to 3 cross 3. So the kernel will be a 3 cross 3 matrix. And this kernel is something which we can shift in horizontal and vertical for all the entire image. I'll show you. So it's a 3 cross 3 kernel. So when the kernel is placed here, so when the kernel is placed here, so it spans a sub image of this entire image. The set of coordinates spanned by the kernel for a particular position of a kernel is called as the S of xy. S of xy is the set of coordinates for this position. This pixel coordinate, this pixel coordinate, this pixel coordinate, this, and this pixel coordinates comprise S of xy. This S of xy will change if the kernel shifts to or 1 pixel right in its position. So when the kernel is located here, S of xy is this pixel, this pixel, this pixel, this pixel, this pixel, this. So the coordinates of these 9 pixels, comprise S of xy when the kernel has been shifted to here. So while during the spatial filtering, the kernel is placed at a particular part of an image, and a mathematical expressions defining the spatial filtering operates upon the pixel intensities of S of xy to give you a single intensity value that is assigned to the center pixel of the S of xy in the resulting image. Let's say for this position of the kernel, what will do, the expression for spatial filtering will work out on the intensities of this and this, all this 9, this, all this 9 intensities. The spatial filter expression will be a function of these 9 intensities, and it will calculate a single intensity value that will be assigned to in the resulting image to this coordinate of the resulting image. So after this coordinates intensity has been calculated, the kernel is shifted to right, and the same thing is repeated to get the intensity for this coordinate in the resulting image. Then it is shifted to right a bit more by 1 more pixel, and then it continues from left to right, and it is similarly done for the vertical shifts. So in the case of arithmetic mean filter, what it does, it calculates a filtered intensity f cap to be assigned at x comma y coordinate. And what is x comma y coordinate? X comma y coordinate is the coordinate at the center of the sub image that is spanned by the kernel. And f cap of xy is nothing but the mean or average value, the arithmetic mean of the curved image in the area which is defined by capital S of xy. The value of the restored image f cap, at location xy is simply the arithmetic mean of the pixel intensities in the region defined by capital S xy. The mean filter, the arithmetic mean filter, smooths the image, and in the entire procedure of smoothing the entire image using this filtering expression, what it does is smooths it, and in this process the noise is reduced. So noise is reduced as a result of blurring. Then the geometric mean filter. Again, in the case of geometric mean filter, f cap of xy, the intensity at the center coordinate of the subimage in the resulting image, is given by the product of all those intensities that are included in, whose coordinates is included in capital S of xy, that product of all those intensities raised to the power 1 by mn. In this kind of filter, which is geometric mean filter, the smoothing is comparable to the arithmetic mean filter, but the detail that is lost due to smoothing is lesser as compared to the arithmetic mean filter. So geometric mean filter loses lesser detail as compared to the arithmetic mean filter. So geometric mean filter smooths the image, but the detail that is lost, the image detail that is lost is lesser than the arithmetic mean filter. Then comes the harmonic mean filter. The harmonic mean filter expression is given by f cap of xy equals to mn upon summation 1 upon small g of st. A harmonic filter works very well for salt noise, but it fails for a pepper noise. It also does fairly well for Gaussian noise. Then the fourth kind of mean filter is a contraharmonic mean filter. Here you can see the expression is given by this ratio, this summation divided by this summation, and here you will see a parameter capital Q, where Q is called the order of the filter. For positive values of Q, the filter is able to eliminate pepper noise, whereas for the negative values of Q, for the negative values of the Q, the filter is able to get rid of salt noise. In any case, Q has to be either positive or negative. So for any value of Q, either this filter will be eliminating the salt noise or it may be eliminating the pepper noise, not both of them simultaneously. If you place Q is equals to 0 in this expression for contraharmonic mean filter, you will find that this entire expression reduces to the arithmetic mean filter. When Q is equals to 0, this f cap of xy will be same as the arithmetic mean filter expression. One more thing, if you will place capital Q is equals to -1, in that case this expression of contraharmonic mean filter will reduce to the harmonic mean filter. It will reduce to the expression of this harmonic mean filter. So now coming to the order statistics filters. The order statistics filter is that category of spatial filters in which its response is based on ranking the values of pixels contained in the subimage encompassed by the kernel. So order statistics filter, what it does, first it ranks the pixel intensities that is contained in the subimage. In the kernel area, in the kernel region, whatever subimage is encompassed, those intensities are first ranked either in the order of increasing order or in the order of decreasing order. And once it has been ordered and ranked, the ranking itself is used to calculate the filtered intensity value to be assigned at the location x, y. The first kind of order statistics filter, which is a median filter, what it does, it replaces the value of a pixel in the resulting image by the median of all the intensities that is in the neighborhood of that pixel. So whatever intensities are included in the coordinates that is contained in capital S of xy, those intensities are first ranked either in the way of increasing order or in the way of decreasing order, and then the median is found out. The median intensity value is found out, and that median intensity is assigned to f cap at location x, y. F cap of xy is the median intensity of all the intensities that is in the subimage encompassed by the kernel. So median filtering, how it is used? So the kernel is moved left to right and top to bottom to cover the entire image, and for every kernel position it will help you to calculate the intensity for the center coordinate. Suppose the kernel is situated at this place. A 3 cross 3 kernel is placed at this point. So this position will let you to calculate the pixel intensity at this coordinate of the resulting image, because this is the center coordinate for the positioning of kernel shown in the figure. So how to find out the median value? We have to arrange the pixel intensities in the ascending or descending order. Let's say I choose the increasing order. So 1, 1, 2, 3 is there, 5 is there twice, 5, 5, what else? 1, 1, 2, 3, 5, 5, 4 is there, 4 is there, then 6 is there, and then 8 is there. So I have arranged all the intensities in the sub image spanned by this kernel in a ascending order. So 1, 2, 3, 4, 5, 6, 7, 8, 9 elements are there. So 9 intensities. So how I have ranked it. While arranging them in increasing order, I have actually ranked them. This is the first position, this is the second position, this is the third rank, this is the fourth rank, this is the fifth rank. The rank according to the order of magnitude. The median value will be the one which is at the mid position. So this is the mid position. Why this is the mid position? Because this is such position to whose left are 4 elements and to whose right are 4 elements. So the median value is 4. So in the resulting image, this is the coordinate point 0, 0. This is the coordinate point 0, 0. So this is 1, 2, 3, 4. So this position is 3, and this one is 1, 2, 3. So this is a coordinate point 3, 3. So we have actually found out f cap of 3, 3. F cap of 3, 3 equals to 4. So this is how f cap of xy image, f cap image will be constructed by use of this median filtering. Similarly, in the next order statistics filter, which is a max filter, the resulting intensity at location xy in the restored image, f cap of xy will be given as the max of the maximum intensity in the sub image encompassed by the kernel. Similarly, for the mean filtering, f cap of xy, that means at xy location, the central location of the kernel, for the central location of the kernel, the restored image will be assigned an intensity which is equals to the minimum value of all the intensities for coordinates that are within the S of xy, that means within the sub image region. So you should note that this median filter is very helpful in getting rid of both bipolar and unipolar impulse noises, and it has very least amount of blurring effect while it is reducing the noise. Although it is reducing the noise, the blurring is not so much as compared to the mean filtered images. The max filter is helpful in reducing the pipper noise because it assigns the maximum intensity to the center pixel. It has the ability to reduce pipper noise. The dark spots can be reduced. Whereas while using a minimum filter, salt noise can be reduced because it assigns a minimum value in the sub image to the center pixel. So a minimum filter will be helpful in reducing the salt noise because it will find out the minimum value in the sub image and it will assign to the center pixel. The midpoint filter, as you can see in the expression, it finds out the midpoint between the maximum intensity and the minimum intensity in the sub image encompassed by the kernel, and it assigns to the center pixel xy of the
resulting midpoint filter. So midpoint filter is something in between order statistics filter and averaging filter, and it is particularly helpful in reducing the random noises like your Gaussian and uniform noises.
Okay, the last filter we should discuss is alpha trimmed mean filter. This is also a order statistics filter. So first of all, what we need to do is we need to order the intensities in the sub image in a increasing order or decreasing order, and then we get rid of the d-2 lowest and the d-2 highest intensities from the consideration. Whatever intensities are left after this removal of the d-2 lowest and d-2 highest intensities, they comprise the g subscript r of s comma t, and these intensities, whatever rest intensities are there, the mean of those intensities is calculated and assigned to the f cap of xy. When d is equals to 0, this alpha trimmed mean filter is same as your arithmetic mean filter. It becomes same as arithmetic mean filter for d equals to 0. In the alpha trimmed mean filter, if we choose small d is equals to mn minus 1, the filter becomes a median filter. And for various values of d, this alpha trimmed filter is useful in reducing noise where the image has been corrupted by multiple noise types, such as a combination of salt and pepper and Gaussian noise. We should always keep in mind that with whatever filter we use, whatever spatial filter or any other filter we use, in most of the cases the noise is never totally removed, but the effect of noise is reduced somehow by using different filtering techniques.